Okay, welcome to our next topic. This is chapter 12's content on sampling distributions, which is now going to take us even further into inferential statistics, which is the branch of statistics we've already been working with in chapter 10, where what we want to do is we want to take sample data and we want to make generalizations beyond it, right? So we want to take a sample of individuals, measure something about them, and use that data to make an inference about a larger population. So we have started to use the building blocks of null hypothesis significance testing. So we're going to make this a little more formal now. Basically, what this approach does is it says, okay, out there in the world, there is some true population parameter of interest, which we believe is fixed. So it's a single number, it's out there. We just don't know what it is. So for example, in the sign test, that parameter was the number, really was the proportion of AIDS patients that would eat more after THC, but we could think of that as the true number. So the true efficacy of our intervention. Our data, we think of as random, meaning that there is some amount of variability across different samples that we take, meaning that we might take one sample of AIDS patients and find that 9 out of 10 eat more when they're given THC, and we might take another sample and find that 6 out of 10 eat more. So which is telling us the truth? Which is the truth? Is any of that the truth, right? So what we call this is we think of this hypothetical thing as what we call a sampling distribution, meaning that when we take a sample and we calculate sample statistics, what we're actually doing is that statistic is drawn from a probability distribution. And this chapter is going to formalize that a little bit more and use a statistic that we're all much more familiar of, which is the sample mean. So what we're going to learn is we're going to learn some properties of sample means when we use them as statistics to make inferences. So to make this a little bit more clear, what we're going to discuss is this thing called a sampling distribution. It's another probability distribution, and we're going to find out that the one we're interested in this chapter is simply just the normal distribution. But now what it is it's a normal distribution that applies to a value of a sample statistic. In this case, it's going to be the mean. And it tells us, basically, since it's a probability distribution, it can give us information about the probability of any of our observations being a particular mean value under the assumption that the null hypothesis is true. So a sampling distribution is a probability distribution that represents the world in the reality in which the null hypothesis is true. And then we use it. The last chapter, the sampling distribution, was the binomial distribution with p equals 0.5. And so p equals 0.5 represents the null hypothesis being true. And what that did for us is with a sample size of n, and then an observation of some number of people being successes, we were able to derive or make a statement about the probability of a sample statistic, simply just the number of people that went up or down. We could discuss the probability that would happen if the null hypothesis is true. This is what null hypothesis significance testing is all about. Other sampling distributions are well known, but we need to learn a little bit more about their properties to understand them. The real important issue is that because a sampling distribution is a probability distribution, it means that it has, that there's variability, right? It means that when we collect a set of data and we compute sample mean on that data, and then we collect another sample of that same data from different people, the mean is not going to be the same. So we call this sampling error, the fact that there's always going to be a discrepancy between our sample statistic and the unknown fixed population parameter of interest. And the key to, we kind of sidestepped sampling error with the sign test. If we want to use a sample mean, so for example, if we wanted to instead evaluate something about the average number of people or the average amount of calories that someone would eat under the condition that they were given THC, we have to also, in order to do that, we have to estimate on average from sample to sample, how much should the mean value fluctuate? And so this is called the sampling distribution of the mean. And if we continue our example forward, let's say now, instead of just looking at, okay, between when people ate stuff after a placebo pill versus THC, instead of seeing if they went up or down, let's instead do the following. Let's say that we collect a sample of some number of AIDS patients, and we simply just give them THC. We don't give them a placebo. We just do one sample and give them one thing. And we find that on average across these 10, 15, 20 people, that they ate an average of 2,500 calories in the day after they ingested THC. Let's also assume that we know that typical AIDS patients, so AIDS patients who have not ingested THC, that typically in the population, they eat about 2,000 calories a day in some stage of the disease. The issue of sampling error is a question of about how much should we expect, or how often should we expect a sample mean to equal 2,500 calories if the null hypothesis is true. And the null hypothesis is that really, if nothing special is going on about THC, that really the true number of calories that any AIDS patient should eat in a day is 2,000. Right? So in order to evaluate that, we have to ask the question, well, if we look at, let me get this out of the way. I think you can see that. Let's imagine that this is a smoothed out histogram. And what we have here is we have the x-axis represents calorie consumption, right? And what the histogram is actually, this would be from one sample. This would be, we drew, let's say some number of people from this population. So this is all AIDS patients with various amount of calories consumed. The mean would be 2,000. So we take one sample and we compute X bar, its mean. And then we make a second histogram. And this second histogram is a record of, let's say we do this, so we take one sample, calculate a mean, take another sample, calculate a mean, take another sample, calculate a mean. Let's say that we do this, thousands of times, and we plot these sample means in their own histogram. It turns out they're going to have the same shape as the population of scores. So this up here at the top, this is people. This is a histogram of single observations of calories consumed. Down here, we have a histogram of means of samples of people. So sample means of AIDS patients and calories consumed if the null hypothesis is true. Two things we want to know about this distribution. These are both, let's say they're both normal distributions. We already know that we can get a probability or percentile for any normally distributed score in Excel. The way that we do that, or using z-scores, the way that we do that is we know what our observation is, our sample observation X. We know mu and we know sigma. Turns out we can do that for means as well. If we know the sample mean, and we know mu and sigma for this distribution of sample means, then we can do exactly the same thing we do in chapter 9, in chapter 5, right? So let's say again, now that this distribution up here is a normal distribution of AIDS patients in the normal population. The mean of this distribution is 2,000 calories. And now let's say that we know that the standard deviation of this distribution is 500 calories. So this is the bell on the bell curve. This portion here is about 500 calories, this portion here is about 500 calories. So in this middle zone is most people in the population should consume between 1,500 and 2,500 calories. That would be normal, right? What we're doing to do down here is let's now choose, let's say we want to do a study with 25 people. The way we construct the bottom is we imagine that we take an infinite number, or just think of like 1,000, a large number of samples with replacement. Each sample, once we've taken a sample, so we grab 25 people at random here, and we don't do anything to them. We simply just calculate the average amount of calories consumed normally. Then we do it again. Right? We put those people back in and we resample another 25 people, and we calculate their mean. Another 25 people, calculate their mean, so on and so forth. Right? If certain conditions are true, which are going to be true, then we can expect that across all of these sample means, the average mean calories consumed should be equal to the average calorie consumed, right? Because if you're sampling a bunch of people and computing their means, and they're all drawn from a population with a mean value of 2,000, then the expected value for any sample mean should also be 2,000. So that's pretty easy. So in this chapter, the mean, or mu, for a population of scores is going to be the same as the mean of the distribution of sample means drawn from those populations. The only math we have to do is the following. What we'll need to be able to make probability statements about sample means is that we're going to need to know what the standard deviation of this bottom distribution is. Well, it can be proved, and we're not going to have to prove it, that this standard deviation down here is equal to the standard deviation of scores 500 divided by the square root of the size of your sample, which in this case is 25. Right? This is due to what we call the central limit theorem. And the central limit theorem basically is that one of the consequences is if you know what mu and sigma are for any measurement you're going to take in a population, then this is just restating the other slide. The mean of the sampling distribution of the mean of the sampling distribution is equal to the mean of the population distribution. The standard deviation of the sampling distribution is equal to the standard deviation of the population of scores divided by the square root of sample size. Now this is important. We call this the standard error of the mean. And this is a measure of sampling error. This is a measure of how much we would expect sample means to fluctuate from sample to sample. And it has an intuitive form, which is that imagine that we choose larger and larger samples. So this denominator gets larger and larger based on how big n is. Anytime you increase the denominator and keep the numerator the same size, the result gets smaller and smaller and smaller. So that means with larger and larger and larger samples, larger and larger sample size, we could expect our sample means to bounce around less and less and less and less. So the standard error of the mean is smaller when you have a larger sample size. Connecting that to sampling error is just, again, the natural fluctuation of sample means. Like we wouldn't expect every time we take a sample of 25 AIDS patients for their calorie consumption to be exactly equal to 2,000 calories. Sometimes it might be like 1950, other times it might be like 2120. So this standard error term, the standard deviation of the sampling distribution of the mean, gives us a number that tells us on average, just like a standard deviation, on average, how far from the expected value should a sample mean be. And that number gets smaller and smaller as our sample size gets bigger, which makes sense because as our sample size gets bigger, we're including more and more of the population in our sample. And so one would expect that the error that is incurred by sampling is smaller because we've got more of the population, right? Okay, so that's a lot of theory. The important component is that we're going to want to use these relationships to evaluate results. Okay, so let's first just work on standard error. So again, if we have a sample of 25 AIDS patients, and we know that, or at least we can say confidently from past research that on average, people with AIDS generally eat about 2,000 calories per meal, or that should be per day, with a standard deviation of 500. What are the characteristics of the sampling distribution of the mean, X bar, when n equals 25? Well, all we have to do is say, well, the mean of this sampling distribution is just equal to mu, it's 2,000. Right? And then that's true for every example in this chapter. So that's the easy part. The other part is then we say, well, what's the standard error or standard deviation of this sampling distribution? Well, we follow the formula. We take sigma, 500, and we divide by the square root of sample size. So our sample size is 25. Square root of 25 is 5. 500 divided by 5 is 100. Right? So this distribution, so basically this says that we could expect that when we take a sample of 25 people, the sample mean, the average amount of calories consumed within that sample, the most likely value for it would be 2,000, and then we would expect it to fluctuate on the order of about 100 calories, rather than when we take a single person and look at their number of calories, we should expect a fluctuation of about 500 calories from person to person. The 100 is saying from sample to sample, when sample size is 25, we should expect sample means of calories consumed to bounce around on the order of about 100. So there's less variability when we're looking at distributions of sample means and looking at scores. This is always true for normal distribution problems. And this gives us a very important relationship, which is that as n increases, standard error decreases. And that's very important for later on some other things that we're going to talk about. But that's a nice thing to know. So as we increase sample size, we expect that the fluctuation from sample to sample in the sample mean should decrease. So should get closer and closer to the null hypothesis value. All right, so why do we care? Well, this means that now what we can do is we can start to think about experimental data in which we actually compute sample means. We'll later extend this to results to designs like the one that we previously used. Right now, we can only do what's called a single sample test, but this is a very valuable step because it turns out that this is what you're doing essentially when you evaluate the significance of a correlation coefficient or something in regression. So what we do is we use what's called the Z test or the normal deviate test, which all it does is it updates the Z formula. Instead of X, as we usually had, we have X bar, a sample mean. We have mu sub X bar, which is just equal to the population mean. And then we have sigma sub X bar, which we learned is standard error. We learned that it's sigma divided by the square root of n. We can use it whenever we're in a situation in which what we're measuring in our sample is a statistic or measurement for which we know what mu is and we know what sigma is. For example, if it was an IQ test, we generally know that mu is 100 and sigma is 16. So what we need to have that set in place. We have to measure all people in a sample of some size with that same test. And either the sample size has to be greater than 30, or the measurement, like IQ, for example, that we're taking, we have to make sure that it's definitely a normal distribution. Now, the good news is that you don't even need to worry about this formula. Because now with Excel actually does the calculation for you. All you need to do is feed it the 3 parts. So we're going to take a look at this. The first thing, though, that you need to be able to do, so what we're going to do is just like last time, we're going to want to return a p-value, or what we're going to want to know, what's the probability either one-tailed or two-tailed, of getting our sample result if the null hypothesis is true. To properly do this in Excel, you first need to ask yourself, is the sample mean that I have, is X bar greater than or less than the mu, the null hypothesis mean? If X bar is less than mu sub X, you can use regular norm dist. And what you're going to do is norm dist asks you for 4 things. It asks you for the X value of interest, the mean, sigma, and that cumulative component. And so it turns out we can sub in things that we know for those 3. And we get our answer if X bar is below mu, we can use norm dist directly. If X bar is greater than mu, we have to do what we practiced in chapter 9 a little bit. You have to take 1 minus that. So let's take a look at some examples for this. Okay? Oh, right. We're also going to set an alpha value, and as before, we're going to decide whether to reject the null hypothesis or not if our p-value is less than alpha, right? Okay. First example. Imagine you're a superintendent of public schools and you've conducted an experiment to investigate whether the reading proficiency of the high school seniors living in your city is deficient. Okay? So what you do is you take a random sample of 100 high school seniors and you give them, and you look at their reading test scores, and you find that the mean reading test scores in this sample of 100, so X bar, is 72. You also know that the national norms, so the population parameters for this test in high school seniors, it's normally distributed with a mean of 75, so mu is 75 for this test, and a standard deviation sigma of 16. In this situation, what we're going to do is we're going to use the normal deviate test or the z-test to answer the question, is it reasonable to consider the 100 scores a random sample from a normally distributed population? So what does this mean? We're basically asking, we're doing the following. We're basically saying the national norms, the mu of 75, that stands in for our null hypothesis. If our school district does not have deficient reading in high school seniors, then any sample that we take of high school seniors should have a mean close to 75. Right? So we're asking, is it reasonable to consider our 100 seniors a random sample from this distribution? So is the 72 consistent with the null hypothesis, or is it inconsistent? We're going to start by just using a one-tailed test. And here's how we would do it. Okay? In the book, we would use the Z transformation. So the first thing that we want to do, and actually it's not here, but we want to understand that what we feed to Excel is we feed X in there, right? So 72 is our X. 75 is our mu, right? That's the null hypothesis. Notice that we don't put 16 in there. We put 1.6 as our standard error. Why do we do that? 1.6 is our standard error because the population standard deviation is 16. Sample size is 100. And standard error is standard deviation divided by the square root of sample size. So that's 16 divided by the square root of 100. Square root of 100 is 10. So 16 divided by 10 is 1.6. Now you don't have to do this part. If you did this part, you'd get a z-score of negative 1.88, but that doesn't matter, right? We see that we just put those 3 numbers into norm dist with true, and notice that our sample mean is less than mu. So this is actually our p-value. This is our answer. Our one-tailed probability value is 0.0304. So it's a little off from the table in the book because the table in the book is less precise. But I want you to look at this picture. This is essentially what we're doing, right? With norm dist. Norm dist is giving us the proportion of the distribution, of normal distribution, from all the way at the bottom up to where we are. And since our sample statistic, our sample mean, is less than the mean of its distribution, norm dist gives us our tail probability. If we had found a sample mean of like 78, we would have had to do 1 minus norm dist to get this upper part. Okay. So once we get that p-value, now we're doing a one-tailed test, so we don't have to multiply by 2. We simply compare our one-tailed p-value with alpha of 0.05. We notice that it's less than alpha, so we can reject the null hypothesis. And again, what was the null hypothesis? It was sort of phrased weirdly, and we didn't state it explicitly. And I stated it sort of in the title of the slide, but the null hypothesis was that mu is equal to 75, meaning that the null hypothesis is that our district is not deficient, right? But we found that our sample mean is inconsistent with that null hypothesis using our procedure here, because the p-value is less than alpha. So we reject, and then we can make a statement that, well, it looks like our high school seniors are deficient, so we may want to do something to bring their test scores up. All right, so the nuts and bolts of the procedure are, we kind of skipped over this quickly. First, you're going to want to calculate standard error. And then but you don't have to do the z-score calculation. I show this to you just to show you what's going on in the background. All you need to do for Excel is you need to know what x bar is. That's going to be given to you, but you could calculate it. Mu, which is given to you. And then you have to compute standard error, again, using this formula. Right? So additionally, these are the assumptions of the test. So we don't want to forget about those, but all our examples are going to be there. So what we say is the null hypothesis is that an expected sample mean is just equal to the population mean for a single sample z-test. And then in order to evaluate the probability, we need standard error. And standard error is gotten by taking sigma, population standard deviation, and dividing by sample size. So you need to know those 4 things. You need to know the sample mean. You need to know your population mean. You need to know sigma and the square root of n to get standard error. Okay? The second thing you need to do is to use Excel, and to use it the right way, you've got to make sure you know, is my sample mean less than or greater than mu? If it's less than mu, then you can just use norm dist directly in the way that we previously learned, subbing in standard error for sigma and x bar for x. If x bar is greater than the population mean, you have to do 1 minus norm dist, and those will get you one-tailed p-values. So if you need a 2-tailed p-value, you have to multiply by 2. Okay? So let's do 2 more examples just to solidify this, and then we'll be done. Okay. So university president believes over the past 5 years, the average age of students attending his university has changed. To test this hypothesis, an experiment is conducted in which the age of 150 students who have been randomly sampled from the student body is measured. The mean age of that sample mean, is 23.5 years. A complete census taken a few years ago showed that the mean age of the population of students is 22.4 years with a standard deviation of 7.6. So let's go through and now bring us into the realm of chapter 10. Let's state an alternative and null hypothesis, and then use the z-test. Basically, what you want to do is use Excel to get a p-value. And in this time, we're going to do a 2-tailed test. We're going to compare to alpha. So if you want to, pause the video and try to work this out for yourself, and then we're going to work it out in a second. All right. So first things first, Now we have a more familiar alternative hypothesis. It's stated in there. Students' ages have changed over time. So notice we're not saying up or down. It's not directional, right? It's changed over time. So then our null hypothesis is that students' ages have not changed over time. And of course, if they've not changed over time, then mu should apply to them, right? That our sample mean should be equal to mu. That's the null hypothesis. So then we want to use the z-test, right? And so the way that we do that is we identify the parameters we need. Then we figure out how to use Excel. And then in this case, we're going to do the two-tailed test. Right? So the first step is we know what X bar was. It's given to us in the problem. It's that with the 150 person sample, the average age is 23.5 years. Mu sub X, or the mean in the population, the null hypothesis mean, is 22.4 years. Again, that's given in the problem. It's coming from a census. Then we have to work out standard error. And again, we take sigma, which was given to us in the problem as 7.6, and divide by the square root of our sample size. Our sample size is 150. Square root of 150 is 12.25. If we divide 7.6 by 12.25, our standard error is 0.62, right? So it's much smaller than 7.6 because our sample size is so big. Next step, to get our p-value, we need to get it directly, we want to use the correct command in Excel. So we check if our sample mean is greater than our population mean, and it is. So when it is, right, or if it's not true that the sample mean is less than you, right? So it's not true that 23.5 is less than 22.4. Then you would use that 1 minus norm dist to get the area above, right, in the tail. So again, note what we type in, right? X bar goes first, 23.5. Mu goes next, 22.4. Standard error goes in as sigma, not 7.6, but 0.62. And then true is always there, so we get cumulative. So if you do this correctly, you should get 0.038 as your one-tailed p-value. But we want to do a two-tailed test. So we have to multiply that by 2. We get 0.076. Now notice at two tails, our p-value is greater than alpha 0.05. So in fact, we can't reject the null hypothesis. So the data are consistent with a non-significant change in age. So stated differently, it doesn't look as if age has changed significantly. It doesn't look like the students are getting older or younger in any significance. Stated another way, a sample mean of 23.5 is within the sort of the sampling error range of the null hypothesis value. So it means at 23.5 as a sample result, we can't distinguish that reliably from just regular old sampling fluctuation due to sampling and nothing else, right? So that's essentially what we're doing. We're asking a question using probability theory, is basically a way to figure out, is our sample result sort of reliably due to something other than just sampling error? And in this case, it doesn't. That we're sort of our conclusion is that we don't really think so. We can't be absolutely sure, but it doesn't look like it. Okay. So let's do one more. Okay. In this example, we'll use something that, by the way, what you're learning now is applicable to industrial design and experiments. So let's imagine that you work for a gasoline manufacturer and they believe that their new additive is going to result in an increase in miles per gallon. Now that's a directional hypothesis, but we're going to be more conservative. We're going to test it as a non-directional hypothesis. So the way we do this is, of course, we need some plausible population values and sample values. So first and foremost, we get our population values actually by collecting what we call normative data. So a large number of mileage measurements without the additive have been made by the company such that that population mean is 24.7 miles per gallon. Right? So this is for basically for cars or driving, and a standard error of, or standard deviation, excuse me, of 4.8 miles per gallon. So we let 24.7 be mu, our population mean, and 4.8 be sigma, our population standard deviation. Our sample data consists of a sample of 75 cars. This time, we've used the new additive, and we find that on average, these 75 cars get an average of 26.5 miles per gallon measured under the same controlled conditions as the other stuff, okay? So now we're going to do it again. We'll state an alternative, state a null, and then we'll test this result with the z-test. Okay. So again, even though initially it was phrased as a directional hypothesis, we're going to test it as a non-directional. So we're going to just say the additive changes miles per gallon. The null hypothesis is that the additive does not affect miles per gallon. And we're going to use the z-test just the way we did it before. So we'll use 0.05 alpha again, and we go through our steps. So again, if you want to stop and try to do this again on your own, try it and then look at the results. So we do this, it's the same procedure, right? Our sample mean is from those 75 cars, and we find with the additive that MPG is 26.5 miles per gallon. Without the additive, the population mean, the normal sort of thing we can expect if the null hypothesis is true, would be that the cars would get 24.7 miles per gallon with a standard deviation of 4.8. So we use that 4.8 standard deviation and our sample size to compute standard error. So standard error is quite small. So again, we would expect natural fluctuations around 24.7 when we take a sample mean of size 75. We would expect sort of, you know, normal ho-hum deviations from mu to be on the order of about a half mile per gallon. Notice we're almost 2 miles per gallon away from the null hypothesis value. And look at how that translates. Our p-value is very small, meaning that 26.5 is a very extreme result. It's a much higher MPG than we would expect under just sampling error. And the probability of in one tail of getting of measuring 75 cars and having their sample mean be 26.5 or more, right, is 0.0005. So that should happen about 5 times out of the 50,000 tests. Right? So that's not very much. We've got to make this a two-tailed p-value, so we simply multiply by 2 and we get 0.001, and 0.001 is very much smaller than our alpha. So again, we can reject the null hypothesis. The new additive definitely affects MPG, or at least we think reliably it should affect MPG if we put it in cars. And indeed, it improves it, right? We go up by about almost 2 miles per gallon, okay? So all we want to do in this chapter is just to execute this test. And note that we're not actually calculating a z-score at all. Excel does it behind the scenes in the norm dist function and then returns to you the p-value that you would have used the table to look up. Okay, so the things to work on in this chapter are the mapping between mu from the population and mu sub x, and how we turn sigma and square root of n into standard error, and then how we use that to test a hypothesis about a single sample from a normal distribution. Okay, all right, that's it for this week. We'll see you next week.